Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to nanoHUB-U's second online course. As you know, the first online course is entitled Fundamentals of Nanoelectronics Part 1, and this is Part 2. So as you may imagine, there is this, thematically we are talking of the same kind of material, same kind of subject matter. And one of the first questions I often get is, well, if I haven't taken Part 1, or maybe I am a little blurry on what we talked about, is that fine? And what I want to start out by mentioning is that there are certain parts of Part 1 that would be useful, or I'd say even necessary background. And specifically, it's the lectures 1 to 5 of the notes. And for the spin transport part, it will be lecture 14 of the notes. And these will all be made available to you as soon as you register for the course. Okay. Now, as for the level of the course, just like with Part 1, our nanoHUB-U's philosophy is we try to make this broadly accessible to students in science and engineering. So we try to avoid specialist jargon. On the other hand, these courses are not survey courses. They are, serious courses that address deep questions. And I do assume a good mathematical background, namely, calculus and differential equations, as in Part 1. In addition, in Part 2, you would also need some background in matrix algebra, specifically eigenvalues and basis transformations. And again, if you don't remember it, that's fine. We'll talk about it. But if you haven't heard about it before, then that could be a problem. Now, getting on to the subject matter then. As you know, these courses are based on this idea of this bottom-up view. And that is, as I said, the developments in nanoelectronics over the last 40 or 50 years have driven electronic devices continually to smaller dimensions. And if you think about a typical, very simplified schematic of an electronic device, we could draw it something like this, where you have a source and a drain. These are the two contacts across which you apply a voltage, and they are connected by this channel through which electrons conduct. And the channel length today in transistors, as you know, every laptop has these billion plus transistors in it, nanotransistors, and each of them is extremely small, which is why you can fit a billion in there. And if you looked at this channel length today, it would be somewhere around here. You see, like 1/10 of a micrometer or so. And that is like a few hundred atoms. And our understanding of current flow, however, is usually based on much bigger resistors. That is, when you start from big resistances, that's where our understanding evolved from. You can write resistance in terms is proportional to the length, and there's this resistivity. And this is the kind of formula you'd have seen in a typical freshman physics course. And usually this is what our understanding is based on. And so when you get to these small devices, you tend to use this to try to understand what's observed here. And that, as I've stressed, is usually rather difficult, because one of the seminal results of these small device conductors is that when you get to a small ballistic conductor, ballistic means one in which an electron gets from source to drain like a bullet, goes straight through without scattering in between at all, and which is very different from what happens in big devices where an electron kind of follows a random walk from the source to the drain. So when you get to these ballistic conductors, actually resistance can be written as a fundamental constant, this quantum of resistance, H over Q square, which is like 25 kilo ohms, of the order of 25 kilo ohms. And then divided by a number, m, whose significance is something we talked about in part 1. That's in lectures 1 through 5 of the notes, actually. So this is what you get in small ballistic conductors. And if you're trying to understand this from the point of view of this Ohm's law, or this thing that you usually have learned in freshman physics, it looks very puzzling, because after all, you think that, well, if length went to 0, well, resistance should go to 0. Why should it go to this quantum of resistance divided by m? Now, on the other hand, if you take a bottom-up view, that is, if you start from here, and that is what we did in part 1 of this course. We started from here. And what I tried to show is that while this applies to a very short conductor, if you had a long conductor, you could write the resistance as this times 1 plus length of the conductor divided by the mean free path. And so for a short conductor, which means the length is much less than a mean free path, you can drop the second term. If you have a long conductor, many mean free paths long, you can drop the first term. And then you get a resistance that's proportional to length. So this gives you a whole different view of resistance and current flow. And that is kind of what I tried to convey in part 1 of this course. Now, one of the important points I want to stress is this: why is it that the bottom-up view gives you it definitely gives you a different view of how current flows, but it's also something that is relatively simpler to understand. It clarifies many concepts. And this is the point I want to repeat again, because this is an important point. And that is that, you see, what was rather confusing back in the 80s, before people had actually studied all these ballistic conductors, was the following. That the idea was that if an electron went from source to drain ballistically, what that means is, well, doesn't interact with anything, just goes straight through, doesn't interact with the surroundings, then how can such a resistance, how can such a conductor have any resistance? Because you see, what is well known is whenever current flows through a resistance, there is a I squared R loss of heat. That is, heat is generated. In fact, that's how light bulbs work. A light bulb is basically a resistor. You run a current through it, and if you run enough of it, it gets hot. And at some point, it emits light. So any resistor, of course, there's this I squared R. That's well known. Okay, now how is heat generated? Well, as the electrons go through this thing, they interact with the solid, and they give up energy to the solid. So all these atoms, which are frozen in their positions, when the electron goes through, they start jiggling around their mean positions. You see? And that's heat, basically. So, but for heat to be generated, the electron needs to interact with the solid. And the point is, if you have this view that electrons go right through without interacting with anything, then how can heat be generated? And if heat's not generated, how can you have a resistance? So what is now very clear is that, well, in an ideal elastic resistor, so that's what we call something like this, that as it goes from source to drain, the process is elastic. Elastic means no exchange of energy. In an elastic resistor, all the heating takes place at the ends. So when the electron goes out into this contact, it has a lot of excess energy, which it gives up to that contact. Similarly, here, when the electron leaves, this empty spot, it is filled up by electrons, and again, there is all this heating here. And there's good experimental evidence that indeed small conductors behave this way, in the sense that in carbon nanotubes, people say that, well, with the amount of current we are running through it, if all the heating were happening inside, then it would have burnt up the carbon nanotube. And the feeling is the reason it's not burning up is because the heating is appearing in the contacts, which are big things that can get rid of the heat. Now, the point I stress is that this division of an elastic part and a part where heat is generated. That makes this kind of resistor conceptually much simpler than what we are used to. And that is because, you see, this process here, this elastic process, that is by nature very different from what happens at the ends. This is what you might call is described by mechanics. Okay, let me write capital M here. So this is like mechanics, whereas what happens at the ends, you could call something like thermodynamics, the flow of heat. So these are two very different branches of physics, you see, which evolved centuries apart. In the sense, mechanics, as you know, started with Newton's laws, which were obtained by looking at the planetary motion in the skies. And several centuries later, heat engines came along, and people figured out that, heat was actually a form of energy, and you could convert heat into work, etc. And it took much of 18th and 19th century, actually, to put all this together. And one of the people who played a very key role in this was Boltzmann, whose name you see everywhere in this field. And that is, who put together this mechanics, which you might call Newton's laws. And he added to it these thermodynamic processes. You see, technically you'd say these are processes that are driven by entropy. And if you haven't heard the technical word, don't worry about it. We'll talk more about it actually in week 5. But what he did was this Newton's law, which described mechanics, to that he added these entropic processes. I guess just to keep the color coding the same, let me write the mechanical part in red and the entropic part in black. And created what's called the Boltzmann equation. And this, what he did here was very subtle, caused a lot of debate in his days, and even today people argue about this, but it is generally accepted as the starting point, standard starting point for all semi-classical transport theory. That is the flow of all kinds of things, electrons, neutrons, photons. People use Boltzmann equation. But it is what you might call statistical mechanics. In the sense it's mechanics, and then there is the entropic processes added to it. And I guess we're talking about non-equilibrium statistical mechanics. And this is the starting point, as I said, for all of semi-classical transport theory. And what we did in part 1 of this course is we obtained a lot of results, things like thermoelectric coefficients, conductivity, diffusion coefficient. Many of these things we obtained in a relatively elementary way without getting into this Boltzmann equation, because this takes some time to get used to. It takes several semesters to actually get familiar with it and do all this, which we didn't really do. We got it in a relatively elementary way. And what made it possible was this idea of an elastic resistor, because, you see, the mechanics and the thermodynamics in an elastic resistor are well separated. Whereas, usually what happens, what makes transport so complicated, what takes time to get used to this Boltzmann equation is because the mechanics and the thermodynamics are all mashed up. It's like intertwined. Whereas here it's nicely separated, and that really made it very simple, because this thermodynamics part, this entropy-driven part, we can actually handle in a very elementary way. That is, all we say is, well, there's always these thermodynamic processes that continually restore the contacts to equilibrium. So whenever electrons come in from a contact, they are described by this equilibrium distribution function, this Fermi function. And just with that one statement, you sort of bypass all the details of what really goes on inside this contact. And that's what kind of made this whole thing relatively simple. Now I might say, well, but that only applies to really small things. How can you obtain any result that's relevant for big things out of a discussion like this. And that's where I guess in the part one I had mentioned that conceptually you could do it approximately at least by thinking of a big device like this as a bunch of little elastic resistors kind of connected in a chain, like what an electrical engineer would call putting them in series. So it's like, this is an elastic resistor, that's another one. So if it's a long thing, think of little elastic resistors like this in series. And with that picture in mind, you could actually use or extend a lot of these ideas, a lot of the results, to big devices. Now in this course, what we'll be doing is somewhat the same thing. You see, we'll be talking about elastic resistors, but we're doing now the quantum version of this. And in quantum version, of course, instead of this Newton's law, we have the Schrodinger equation. See? And the Schrodinger equation, maybe I'll just write this here. Schrodinger equation. And to that, of course, you have to add the entropic part again, this entropy-driven part. And the resulting thing is what sometimes people call the quantum Boltzmann equation, or this NEGF, non-equilibrium green function method. Yes, there is usually this, as I'll explain, involves the works of many people, which is why this name is somewhat impersonal rather than just Boltzmann. There are many people involved in this work, and the name is this non-equilibrium green function method, which is what we'll be talking about in this course actually. And what you might wonder is, well, this sounds like fairly difficult stuff. It's non-equilibrium quantum statistical mechanics. Okay? So how are we doing that in 5 weeks? And again, what allows us to do it, as I'll explain a little bit right now, is this idea of the elastic resistor. That is, you see, if you look at the Schrodinger equation, you have, those of you who are not familiar, even you have probably seen something like this. See, E psi equals H psi. And that H is usually a differential operator. As we'll discuss in this course, in week 1, I'll explain what that operator looks like and how you convert it into a matrix. And most of the course will be using the matrix version of this. But the point is this Schrodinger equation as it stands looks something like this. And that's just the Schrodinger equation. But then to analyze devices, of course, what you need is something that includes these entropy-driven processes, or the contacts here. So we need something that will use the contacts and will describe the contacts. And this is where, I guess, what we'll show is the contacts can be incorporated through these 2 extra terms. So this is the part that represent the effects of the contacts, which is where all these entropic processes are. See? And now you might say, well, that doesn't look like something totally different. That sounds like a modified Schrodinger equation. What's this NEGF? Well, the thing is that, you see, you cannot quite use this equation directly. Or rather, if you use it, you have to be very careful. And that is because, you see, supposing you have 2 electrons coming in from 2 contacts. You know, you have one contact, the source, and another contact, the drain. So let us say if you had electrons come in from the source, which gives you a certain S, and that we call S1. And the result is, as a result, you get a wave function that we call psi1. And then you have a source 2 due to the drain. So this is the source contact, that's the drain contact. And you have another S2, which gives rise to a certain psi2. Now the question is, what would happen if you had both present? And if you use this equation, of course, you would come to the conclusion that you should add the 2 wave functions. And that would be wrong, you see. What you should add is actually the wave function squared, you see. Something like this. You should be adding this times this conjugate transpose actually, which I write as dagger, So you have to add those two things. And in the case of light, you see, there are two types of sources. There's ordinary thermal light bulbs, light sources, where when you have two sources, you add the power. 40 watts makes 80 watts. But you don't add the electric fields. On the other hand, if you have a laser source, then you can actually add the electric fields. So there is these two types of things, the incoherent thermal sources and then there's laser sources. With electrons in normal solids, you only have the equivalent of a thermal source. You don't really have a equivalent of a laser source. Although in superconductors, the electrons, you could say something that is more like a laser source. But this is beyond the scope of this course. If you're interested, you could look at this Feynman Lectures Volume 3, like the last chapter, I believe. But the point is that with normal electrons then, it is not very convenient to work directly with this equation, with the size, just because when you have multiple sources, this equation would tend to add the size. And so you have to be careful that you have to treat each source separately, find the psi dagger, and then add it. So instead, we have these NEGF equations, which we'll, I guess, talk about in week 2 of this course. I'll explain, which directly relates this psi dagger. So it takes this psi dagger, which this is the quantity that we'll write as Gn. And in the literature, this is often written as G less. Actually, what I call Gn is like minus I times G less. But so the psi dagger is like Gn, and that is related to the strength of this S. So there's a SS dagger, which we'll write as sigma in. Again, in the literature, that's like sigma less. And then there's a GR and GA. And this is the basic equation of this NEGF method, the non-equilibrium green function equation. And this Gn is this non-equilibrium green function. So that's what we'll talk about in, I guess, week 2 of this course. And then in weeks 3 and 4, we'll look at many examples based on this and get a feeling for how to apply these equations to real devices. But here again, let me make the point that this is, non-equilibrium quantum statistical mechanics. This originated, this whole thing started back in the 60s with the work of many people, Schwinger, Kadanoff, Boehm, Keldysh. In fact, this equation, although the notation is a little different, you can see in a 1965 paper by Keldysh, Chile. And the difference is, and that of course required fairly advanced formalism. You see, it involved many body perturbation theory, which takes many semesters to master. So again, how are we doing this in 5 weeks? Well, again, because we are applying it to an elastic resistor. So we're not getting into many body perturbation theory. We are doing it straight from a one-electron Schrodinger equation. And we show how you can use this to understand all kinds of different experiments that people are doing at this time involving like conductance quantization, quantum Hall effect, and spin transport experiments. So that's what we'll be talking about in weeks 2 through 4. And in the final week of this course, I'd like to end with by saying a little more about these entropy-driven processes. You see, because as I said, the power of the elastic resistor approach is in a way that you don't have to get into the details of this. That without understanding these entropy-driven processes, you can still go ahead and get a fairly good description of things. But I want to use this last week to give you a feeling for what makes this kind of process fundamentally different from this kind of process. The entropy-driven things from the force-driven or mechanically driven things. So what's the difference there? And I use this especially to also discuss a little bit about a problem that's of current interest, which is widely talked about, and that is the relationship between information and energy. That is, you see this word entropy in the literature you'll see in 2 different contexts. One is in thermodynamics, what's called the thermodynamic entropy, And that entropy has the dimensions of this Boltzmann constant. It's like joules per Kelvin. It's actually got a dimension. Another context you'll see the word entropy is the Shannon entropy for defining the information content of something. And that's a dimensionless number. See? And there's a lot of discussion about the connection between the two. You see, everyone realizes that physically they're talking of something similar, but exactly what is the connection? And here I'll try to give you some of our perspective based on, again, this elastic resistor concept, actually. So that's what we'll do in week 5. And I figured, that would be a good general note to end this set of courses in. And so thank you and welcome to nanoHUB-U's second online course.